Okay, welcome everyone to our last and final session. Uh, this is mostly going to be an open house. I have folks in the room and I have folks online. So why don't we get started with a quick poll? There we go. So please take this poll. Oh yes, you cannot see the poll, can you? So I'll ask, well, offline, I'll just ask you to raise your hands. Did you attend the probability workshop, the full workshop on day one? No, no. Okay. Yeah, yeah. Online. Okay. And did you attend the second day decision analysis? Oh, you haven't registered. Okay. So this is the first time you're coming. Oh, got it. Was not coming? Polling. Yeah. You have to open the polling tab, by the way. For those of you who are on WebEx, on virtual land, please open the polling tab. So I have 13 people responding. 16. We have 24. $17. Can not those who have not started, can you please open the polling tab? Yeah, 21, 18. Okay. So we have six more people. It's if you look next to your chat, you'll see on the right side at the very bottom polling. If you can please open that, then you'll be able to take the poll. Okay, 18. We have six more people. Six more people. Can you find the polling tab? Five more people. Very good. Five more. Please find the polling tab. It's at the very bottom right. It's next to the chat. Five more people not started. Six more. Okay. Please find the polling tab. Very nice. 20 people have managed to find it. Thank you. Five more people, look at the bottom right of your WebEx window and you'll see it polling. Sometimes it could be hidden with dot, dot, dot. Okay, I'm going to start closing the poll now. 20 seconds, please finish up. So it seems like 18 of you are all caught up and or 18 or 17. One person hasn't caught up and has not watched, I guess. I don't know if it's the same person on both. So whoever, if you have not seen anything that I've shown in the last 2 days, this will be a very difficult session for you. It might be better to just not attend this, just watch online and catch up. But for everybody else, we should have a lot of fun. Okay, let's get started. I'm going to give you one more poll now. Oh, sorry, 1 second, something happened here. Give me 1 second. Got it. There we go. Okay. So this is a question for everybody. What words do you use? These are technical words. Which of these words do you use? So the words I'm showing here are, you can see on the screen: random, expected value, risk, and dependence. So please take the poll. For those who just joined, it's on the bottom right of your WebEx screen. Please open the polling tab and you will see the poll. Great, 16 people have taken it. That's great. Let's keep going. 29 people in the room. Let's get at least 25 if possible. 10 people haven't started. Please go to the bottom right and start the poll. Okay, so 19 people have taken it. In the room, for the four of you, do you use the first word random? Have you used the word? Okay. Yes. Oh, so random meaning in technical conversations, do you use the word random? Random numbers. Let's do a random number simulation. Do you use it in that context when you use it technical? Okay, I get the answer. Yes, in the room. Expected value is a term that you will get when you are calculating. It shows up in economics a lot when you're looking at uncertain deals and you're looking at the average value. People use the term expected value. Risk is used very commonly in society, and we talk about it technically. And dependence is when we're looking at two factors that have connection. Okay, so I'm going to close the poll at this point. The last person who's finishing it, please finish up. 20 seconds. Okay, 15. Okay, there we go. Hello. Nice to meet you, sir. Okay, so let's share the poll results with everybody. So here you can see, and make this any larger. So 17 of you have used the word random, 9 have used expected value, 5 are using risk, and 2 are using dependence. And 8, I guess, couldn't find the polling panel. So let's go to the sample topics we can cover, and it's really open to what people want to talk about. So I have a menu of options that you can pick. The first one is about words that I recommend we stop using. And all 4 of the words that I put in here, random, expected value, risk, and dependence, are words we should not be using technically. Then we can talk about simulation, the probabilistic essence of simulation. What is the core theory behind it? Then we can also talk about a new probability distribution called the meta-log, which has changed the way we do statistics. And we can spend a lot of time on inference, on learning theory, review the material we did on day one, and go deeper into beta distributions, maybe reliability, just general open. I really have a full structure, but I have some slides if you want to talk about the words to stop using and the simulation, and the others we already saw from previous days. So maybe you can write in your chat. I wonder if I have a poll for this. Let me just check. No, I don't know, poll for this. So why don't you type in your chat, what do people want to focus on? So which topic? And based on that, I'll spend my time. Which topic do you want me to focus on? So we should open the chat. Any nominations? Madam, feel free to suggest. Yeah, I don't see any chat responses. Probability, okay. Oh, all of it is probability, Vidya Chandru.
Asking which topic, particularly will you make five, sorry, four. Based on that, which one they asking?
Okay. Simulation, all right, we can do simulation. Words to stop using, simulation. Okay, why don't we start there? I've got one nomination for words to stop using, and then we'll go to simulation. So let me do this. Let me ask you this question. What do you mean by the word random? So we use this word all the time. So I want everybody to go on their cell phone, go to dictionary.com or M-W, which is Merriam-Webster. Dictionary is British, Merriam-Webster is American. Go and type the word random and look at the definition and paste it in the chat. No, I'm asking you to literally go to the dictionary and paste it. So literally go to these, dictionary.com. Here, I can give you the links. Go to any one of these two, copy and paste the definition of the word random into our chat. Okay, I see one. Hiteshi, thank you for putting it. Chandrasekhar sir, thank you for putting it. Made, done, or happening without method or conscious decision. Yeah. Haphazard. So very good. Okay, so I'm going to share what I'm seeing. A haphazard course in Merriam-Webster without definite aim. And the adjective form is not what I'm looking at. Well, random adjective is more in English when we say, oh, this is a random topic. And this is not a very good definition with the word random in it, but the other ones apply. And if you look at dictionary.com, as you pasted here, made, done, or happening without method or conscious decision, unfamiliar or unspecified. Okay. So now if you go back to a technical topic, when you call the rand function in Excel or any of your mathematical libraries, okay, in your software code, is it really arbitrary and without logic? Is that true? What do you think? Can you type in the chat? Ushanam, do you want to share? You can share your talk as well. So Dr. Vidya is saying, no, it's not arbitrary. So Dr. Vidya, can you come off mute?
sir.
So why do you say it is not arbitrary? Or you can't hear them, right? Okay. Okay. Why do you say it's not arbitrary?
Because those Excel or any other working platform, it should have the syntax meaning, sir.
Let me get you on the computer. Right. Can you speak again?
In that working platform,
Yeah.
if you write any term, it should have certain syntax meaning.
So syntax it will have.
Yeah.
And can you mute, lower the volume? Yeah. So syntax it will have, but the question is, what does that function do? Is it arbitrary in its logic? Like, can
It's
you predict what it will do?
actually in probability random means each item has same chance of getting selected.
What distribution is that? What is the name of that distribution? You're absolutely
Random
right.
sampling.
No, no, but so you're not. So you're sampling from which distribution? You're correct. It has equal likelihood, but
Yeah.
what is the name given to that distribution?
Is it normal, sir?
No, no, no. Anybody else wants to try? Which distribution is it where everything is equally likely?
Uniform.
Uniform, yes. Yes, yes, that's right. So, in fact, if RAND were truly arbitrary, like the word random suggests, you cannot use it for simulation. It is actually totally wrong to use that word because there's nothing random about random. It is guaranteed to be uniform. So when you call RAND in any computer program, you're sampling from a uniform distribution. That's what you're really doing. And so when we're having technical conversations, it really confuses people, especially lay people, when you say random. Because they're like, random? You mean anything can happen? No, that's not what we mean. We mean very specifically, it'll be equally likely, it'll be laid out very nicely with the uniform sampling. So, so this is on my list of words to stop using. If you're technical, we should never use this because it's misleading and unclear. Let's generate random numbers. Instead, I want to use sentences like, let's sample from a uniform distribution. That's very clear. So, and the principle behind this is we're not just seeking to understand, but also to be understood. When we speak, people should be precisely able to follow what we're saying. Then let's look at the next one. By the way, let me actually, before I jump ahead, any reactions to that? I know random is a very common word for a lot of people. Any reactions? And many of you use it. I'm asking you to stop using it. Any reactions? Everybody's okay with that? Speak now before I move to the next one. I'm getting a thumbs up. Girija, thank you. Uma, thank you. Okay, I'll go to the next one. Expected values. So when you have a 50-50 shot of $100, 100 rupees, 100 crores versus nothing, then we call the average, this $50 number, we call, economists call it expected value. Statisticians also use that term. So the question is, can you ever get $50 from this deal? Is that possible? Can you type in your chat or come off mute? Okay,
No,
Dr.
sir.
Vijay. Yeah, yeah. Who spoke? Sorry, can you come off mute?
Vinay sir here.
Yeah, why can't you get $50?
Multiply with zero, whatever may be the number there, it will be automatically, it will be not be able to get 50. The other one is 100.
Right. So you can either get nothing or you can get 100, but you will never get 50.
So calling it expected is totally misleading, right? So you can either get 100 or 0. So what we use, the term is certain equivalent. Certain equivalent means what is the amount of money for certain that is equivalent to the uncertain deal according to you. So if you had $50, you'd be indifferent between having this money for sure and having a chance to get this deal, right? It's 50-50 short of 100 versus nothing. And that's a very different use of language than saying this is the expected value. Let this sink in. This is a slightly more advanced philosophical argument, but a very practical one, because I've seen havoc created in the industry when people say, oh, I should expect this. No, you should never expect this. So I've stopped using expected value completely. I use average value, probability weighted average, or certain equivalent. These are all better options. Any reactions to this? Is the logic clear? Awesome. And you can give your thumbs up emojis, that also helps. Okay, excellent. So let's go to the, thank you, Dr. Dhananjay, Uma, appreciate it. So here is another one, risk. So I looked up risk, the definition of risk, and it's basically the probability of a loss or a bad outcome. So a question to everybody is, what is the opposite of risk? What is the word in the English language for probability of a good outcome?
Success?
Success has no concept of uncertainty in it.
Safe.
Sorry?
Safe.
Safe. Safe has no concept of uncertainty in it. Anybody? What is the opposite of risk? Some chance of a really good outcome. May occur, but that's too. May occur has no notion of good outcome.
Gain?
Gain has no notion of uncertainty either. Gain is just gain. I need a word which has both uncertainty and an upside. By the way, if you're struggling, that's fine, because I have also not found a word. There is no word. So using the word risk causes very imbalanced thinking, because you feel silly if you say something like, oh, there's a risk of making a lot of money. No, I don't. I want that risk, right? So instead of saying risk, I prefer to use chance, probability, uncertainty, because these are neutral. There's you can talk about the chance of making a lot of money or losing a lot of money, or having adverse outcomes or good outcomes. So this is a very important thing where we keep our conversation in some kind of balance. Because if you don't do this, you can go. I've been in meetings where somebody uses the word risk and suddenly everybody panics. Risk. We don't want risk. Like, calm down. It's just uncertainty, and we have to deal with uncertainty in life. Okay. How's that? Any thumbs up, thumbs down? Give me some emojis there. How are you reacting to this? All right. Just jump in. If anybody feels it's controversial, you want to talk about it, just jump in, get unmuted. Otherwise, I'll keep going. Here's the last one on my list. There are many, I'm just giving you 4. Dependence. Dependence is again a technical term in probability. It's like two variables are dependent. Now, yesterday's example, we talked about shoe size and reading ability. And do you feel questions? Do you feel silly saying shoe size is dependent on reading ability? That just doesn't make any sense, right? But it is true. It is true that knowing shoe size may tell us something about reading ability. Okay. So that is why I prefer the word relevance over dependence. Okay, because relevance is about state of information. Okay, so instead of dependence, dependence has a causal notion to it. Anytime you have any causal language, a red flag should go up because causal thinking is beyond our pay grade. It's very difficult for anybody to establish causality. The most we can say is, hey, if I see something, it may be correlated with something else. At least I don't know why it's correlated, and we want to find out why. So that's the last one on my list. Okay. Any reactions to this? You can give me your emojis. If it's unclear, just jump in and ask a question. And otherwise, you can give me a thumbs up, or if you don't like it, give a thumbs down. Okay. A couple of thumbs up. Thank you. All right. I'm going to go to the second topic you want to talk about, the essence of simulation. So I have a question for you. What is the distribution of the cumulative density function of any distribution? Just to make it a little clearer, let's say there's a very asymmetric distribution here, and it could be for anything, maybe the revenues or the test positivity rate or whatever you want on the x-axis, something that we're interested in the x-axis. Okay, and you're seeing on the left the probability density function, and the right you're seeing the cumulative density function. So the numbers in the x-axis are distributed according to these density functions. So you can see that there's more concentration. If you do a simulation, you should see more numbers in this area than you will see very few numbers here and a sort of a tail here. You'll see some here. So that's what you will see. And that's not uniform by any stretch of the imagination. It's highly asymmetric. Okay. So then the question is, what about this particular graph, the CDF? So as you are going through this, as these numbers are being simulated, right? How will the distribution of the CDF, these probabilities be? How are they going to be distributed? What distribution will this follow, this y-axis? X-axis we know is based on the shape. What about the y-axis? Anybody? Type in the chat, especially those who have, how many, have people studied simulation?
No.
No,
Somebody maybe in
they may have studied, okay.
in some topic they want.
They might have done simulation. So this is the theory behind your RAND function. So whenever you do a RAND and you convert from uniform to any distribution, this is the theory behind it.
Electronics.
They have to do?
They study.
Okay. So I know there are people from, okay. So Madam is saying the electronics folks are studying. So I'm hoping there's some people here.
Computer science nowadays everyone.
Everybody has studied simulation. Okay, so computer science people, electronics people, tell me, how is this axis distributed? Anybody? Dr. Vinay, you're speaking. Go ahead, speak up.
Vinay sir, your voice is not audible.
What is the distribution of this axis?
Yeah.
Is it exponential? Who said, sorry, who said exponential? Oh, Vidyaman, okay. Exponential would not be correct. It would not be correct, no. Any other guess, like what other distributions do you know?
Some parties is asking.
Dr. Vidya, do you want to come off mute? We can talk.
Sir,
Yeah,
not exactly, sir.
yeah. No,
Somewhat it looks like.
yeah. So let me give you a hint. Every point in this axis is directly correlated to some point here. Every point. Okay, so if you see that, what is your intuition on how this axis is distributed? What distributions do you know the names of? What can you try? Think of something.
Yeah. Sorry, sir.
Okay,
No idea.
let me break it to you. This is all going to be uniformly distributed. Uniform. And if you think about it intuitively, how would this make sense? Because you are going to generate numbers, any number here, right? See, you see the small tail here. This is saying that you will not have anything in this, like very few generated in this axis. You have most of it. You have most of it generated in this. That is telling you about the x, right? But what it means is that on the y-axis, the full range of probability will always be from 0 to 100. If it is not 0 to 100, you cannot have a distribution curve. So you have from 0 to 25%, the numbers are going to be from 25% to maybe 37%. So this is the range. Just mute him. Just muted him. Okay. So it's a very important result. And this is the reason you can do simulation, because if this is uniform, we start here by using the rand function in any library to generate a uniform number, to sample a uniform number. And then we can do this is called the inverse, the CDF inverse. So if you take the inverse CDF of any uniform, you will get the X number. That's how you do any simulation. So this is how it works. So for instance, actually now I can switch over to metal log distributions, which are great for showing simulations. We share that. So these are the metal log distributions, and in the chat, I'm going to give everybody a link so you can see this. Yeah,
In which language you execute?
I will show you. I built these figures.
He's telling the mechanical quality control, the TM and mechanical waves. Statistical quality control.
Yeah. Probability has very strong use case in there. Yes, so let me show you how you can very intuitively have that conversation. So I'm using, this is one of the biggest advances. This is one of the biggest advances in statistics that has happened in the last decade or two. And it's by a friend of mine called Dr. Tom Keelan and Dr. Brad Powley. They both did this research on what is called quantile parameterized distributions. And I'll explain what that means in a moment. It sounds heavy, but it's actually very, very intuitive. So if you go to the software tab here, these are all free workbooks. And if you go to the Excel workbooks, this is the one I'll point you towards. So you will just want to bookmark this link. Yeah, I just shared it on the chat. Yeah. So here, it's still loading, I guess. It's still loading the Excel link. There are a couple of different workbooks in this. Why is it so slow? I have one open right now, so I'm going to walk you through this. So imagine, we can try. Madam, what is your name? Madam. So let's talk about your use case. In which department did you say you are? Mechanical engineering. Okay. So you're talking about the failure of some component. So what is the component you're thinking about?
You're taking, diameter of the shaft given, go or no go, number of per hour 50 components are
manufactured. So that
it will take a experiment or need inside the machine.
So, so yeah. So let's talk about the upper limit and the lower limit. What is the unit that we're talking about? Like what is the machine or what is the part?
This auto turn parts.
Auto turn. And it's an auto turn part. And how do you measure failure? Like what is the measurement?
Because we are going to set the tolerance,
Tolerance of what?
the component.
In what are the units of that tolerance?
Dimensions we will check in terms of mm.
Millimeters. Okay, that's what I'm asking. Okay. So in millimeters, how much so it can deviate from what you're looking at, right? So that's great. So let's talk about this tolerance. So this is dimensions of what is the name of the part? Just make something up, some example.
Shaft diameter of 25 mm.
Okay, so dimensions of shaft diameter. So that's the distinction we are interested in. Okay. So now I want to ask you what is the so this on the left side here are percentiles, and on the right side is the actual diameter measurements. I'm just going to make it all blank. So let's start with the low end. If I were to ask you what are the reasons for it being really low?
It's 25 plus or minus 0.5. For example,
Yeah.
5.5 and 24.5. Lower limit.
So you're talking about half a millimeter. So okay, so let's not do symmetric, okay? Because symmetric destroys information. So I want to ask you this from your mechanical experience, and everybody else can also talk about this. So what are the reasons for it being below 25? What could happen?
No, because as the maximum material condition and the least material condition comes now, sir.
Yeah.
So we have to rework, we are retaining maximum material condition during the quality check. We can rework the component. This material condition means we cannot rework. These are wastage. So
Yeah,
comes
but
to the component.
no, but why could it happen?
Error. Maybe
Because of machining errors,
machining errors.
human error.
So machining error or human error. Or this is like over machining, right? Over machining. Over machining. Okay. So, and could it be because, I'm just making stuff up. What you had a sudden spike of electricity, so it just moved faster than it should have. Are those real reasons?
yes.
Okay. So I've got two reasons here. It could have over machining, or human error. All of those reasons could happen. How low is low? That is, any lower than this, you would fall off your chair in disbelief. You wouldn't believe it. What is that number? So 25 mm is what you want, but it's not going to be 25 mm. There has been over machining. I'm telling you, over machining has happened.
That is defect only.
Yeah, it's a defect.
So not-
No, I understand it's a defect. But let's say somebody tells you, oh, over machining happened, Shantana madam, and now they tell you the number. How low should the number be? Any lower, you will not believe it. You'll be like, something is wrong. I don't believe this. No. I'm not talking about the requirement. I'm talking about the actual observation. How low could low be? What have you seen in your experience? If there's a defect, how low is low?
20.5. Other we are not going to accept.
No, you may not accept, but I'm not asking your preference. You're talking in the language of preferences. I'm talking in language of information, like what actually happened. So there's a separate stage of accept or don't accept. But I'm in reality right now. How low could low be? What have you seen in your experience?
It is waste only, sir. How can you say that it's a waste?
No, waste is a human decision, right? Keep that separate. I'm saying how small could it be? Could it be 23? Like, I know you will reject it, but what will the machine do? Like in the milling, the process, how low could it be? So suppose I come and tell you it is 23. Is it possible?
No, sir. We are not going to accept.
So when you say, okay, can you help me compute this?
plus or minus 1 mm or like that?
So I'm asking, so what I'm trying to do, I'm separating two things. One is whether you should accept or not. That's a decision. We're not talking about that. I am talking about what the machine actually does.
We will change the tool set if it is blind or something.
Okay, so,
Extra material we have removed it.
yeah,
So it comes below the requirement.
yeah,
Dimension below the requirement.
yeah.
By observation itself and by measuring itself,
Measuring.
we can separate it. That is the final thing we will do that.
Final-
So, okay, so in a machine that's working properly, what's the lowest you're willing to believe it can come? Otherwise, you will call it defective and you'll change the machine, the milling system, everything. So what is the lowest you can see?
One consideration.
Yeah,
Errors due to machine is one consideration.
yeah.
Many erroring considerations will be there. It may be due to the human errors, or it may be due to the defect in the component itself. Many things. It is not only because of the machine.
So let me ask another way. How many
Okay.
times do errors happen? If you had 100 samples, how many times do you see it's going below 25?
Very often they are going to check. It is depending upon 25 or 50 components per hour it is produced from the
Yeah.
machine. So,
Madam,
regular. there'll be
May
a
I
check.
interrupt?
Yeah, go ahead.
Yeah, madam, actually, what is the accuracy of the instrument? That's what probably Soumik is referring to.
Yeah.
Accuracy
Yeah,
of the accuracy of the instrument in producing the component. Plus or minus like 1%, 2% of the dia, or 1 mm,
So let
0.5
me,
mm.
okay, let me try. This may be wrong, I don't know, but I'm going to try making something up. You tell me if it fits. You might say that in the last 100 times that you've run this, the lowest, so the lowest you have seen, or you've seen at least 10% of the, let's say you ran 100 batches, and each batch had 50 of them. Okay, so we're talking about 50 times 100, 5,000. And of those 5,000, 10% were below a certain number in diameter. What is that number? And I'm going to make it up. Suppose it was suppose it was 23 millimeters.
Probability of failure.
Yeah, no. So let's not talk about probability of failure just yet. I'm saying that you ran 50 batches, and 50 batches, you found that 10% of the total samples produced were below 23 millimeters. Okay, and then of those 50 batches, the median, it's around, let's say, 24 millimeters, and only 10% is above 25 millimeters. Median, you want 25, okay, and 10% is maybe above 27 or 26. What do you want to say? So 10% above 26. Okay, so if you believe this, right, what we just did here was go ahead.
It is skewing towards.
Skewing towards the right. Yeah, so let's change this over here. So this is not percentage, we want numbers. There we go. It's easier to interpret. So what we have is the shape of your belief. And you will see that the CDF, as I mentioned in my comments yesterday, you can read probability from here. So the 3 points you gave are an exact fit on the probability distribution. So that's what the Metal-Log distribution does. It gives you an exact fit to your assessments, which can come from data. It can also come from your intuition. So you give it like this in percentage, like 10% chance of being below 23, 10% chance of being above 26, and 50-50 of being above or below 25. So you give this information, this is what it looks like, and this is what the distribution looks like. And it is, I think you would call this right skewed distribution, I think. And so this can be simulated now. And the nice thing about the sheet is, let's see. So, but just to explain what is happening in the rest of it, you can go more than this. So you can give 25th percentile, 75th. So you can give more inputs, and you can choose how many terms you're fitting. We've only fit 3 terms. You could also say just fit the first 2, then it's not a perfect fit. and you've lost some information. But 3 is good. I have 3 assessments. I want all 3 to be fit. It's not always guaranteed, but if you get it, you get it. Now, if you go down here, you can see the simulation here. So this is a y value, this is an x value. So this theory that I just gave you, that the y-axis is always uniformly distributed, I can use it to generate numbers to represent what you are seeing. And the way I would do that is, I would say these are the y numbers. So and trial, and let's say 1,000 tries. So 950. Let me go down to 1,000. Okay, so these are 1,000 samples I'm going to sample from what you just assessed. Okay, so I'll go back here and I'm going to take RAN, which is really a uniform sample, sampling the uniform distribution. So I'm going to do this 1,000 times. This is my y-axis value. And the nice thing is, what I just did was I sampled equally likely any numbers on the y-axis. I'm going to apply the CDF inverse on this and get the x values from your distribution. So the x, the way we do this is x. This is the data table. So I'm going to drop it in the y, and I'm going to go to data, what if analysis, data table, and column input. I'm going to put it into this one. I think I got the wrong cell though. I think this should be equal to this guy. There we go. So this is telling me, and these are all these are the y-axis, these are probabilities or percentages, and there we go. So the x numbers, so you can see the numbers are all generated from 22 to 25 according to your distribution. So this is a really good one. Now, if I want to find out, is it matching? So I could do the 10th, 50th, and the 90th percentile of this data. And I want, actually, I want this array. And I want to pick this. You know, is it a little hard to see? So there we go. So you can see here from the simulation, just the simulation, if you do, you will see that 10% of the samples will be below 22.8, 10% will be above 26, and 50-50 are above and below 25. So you were just able to use this distribution and generate samples from it. Now, so this is very helpful. So when you're building, if you want to see what will happen with parts coming together, this directly lets you do that. And it is very quick. We just had a 10-minute conversation. We built your probability distribution. This is never possible before. It is very difficult to have this conversation before this tool was invented. So this is a game changer for every discipline in you know, anything that is dealing with uncertainty. So now we can do something interesting as well. Suppose you were to ask, like, what is your, you've given me 10, 50, 90th assessment. But if you want to ask me that, hey, what is your tolerance below which you cannot accept? What is that number?
It's a very point.
No, 24 point.
24.5. Okay, so they are saying 24.5, you cannot accept below that. So now you have to report to whoever is asking, what is the chance that this process, the machine, everything together, will go above 24.5? And is it a band? It's plus or minus 24.5 both sides, right? Okay, so let's talk.
B will be 25.
So probability of being within tolerance is what your business question is, correct? So your thing is, your target diameter is 25 millimeters, right? And then low is Let me put this here. Low is minus and high is 0.5. So you want this confidence interval, or you want the probability of being in this band, basically. So the way to do that is I need to read from this CDF chart that 24.5 to 25.5. What are the numbers on this axis? And the difference between those two is the probability. So let's see, how should we do this? So if I want to read this at 24.5 and 25, so what's the chance of being below these? And let me, so I just need this and this. Okay. So I'm going to do a V lookup. I can do an X lookup. So this number, I'm going to look for it in the CDF chart here. This is the X-axis. And I'm going to look for the return array, which is the probability of being below this number. And if it's not found, I'm going to just report 0. And I'm going to set a loose match, not a tight match. So here we go. So that gives me 35% chance of being what happened there? 8029, 8133. Make this try to just click. Oh, there we go. So 35% chance of being below this. And I want the same logic to be applied to this one. 71% chance of being below 24.5. And so if you take the two, subtract these two, one from the other, you have a 36% chance of meeting the target. That is your answer.
But it may vary time to time. It's not fixed. 36% will not be fixed.
Every half an hour.
Okay, so now we're going into continuous inference.
Yes.
So this is the foundational. So we've got this. This is one way of having that conversation, that suppose you had many runs, then how do you want to infer based on that information going forward? This is one way of doing it. Okay. So, but now you want to do continuous. This is where machine learning comes in and all that stuff. So let's go to that part. So I'm going to show you one more resource, and that's kind of back to the screen of a list of topics. Learning theory, beta distributions. Matlog also has a role here. So in learning theory, we covered this yesterday. So I'm going to give you one more Excel sheet here. Before I do that, I should also show you the tree flip. So you were there in the probability workshop, right, madam? Oh, okay. So you didn't see the inference models then. First day class. Okay. So we did, I would encourage you to watch that video. So in the first day's class, we talked about inference. I'll give you one. Your problem is a pretty nice one. I can talk about the whole of probability theory in different aspects of it. So I'll switch to discrete inference first. So discrete inference is, let's say you saw 7 heads in a row. What is the probability of the next coin landing heads? People in the audience should know this. Because you see 7 heads in a row. What is the chance that the next coin lands heads? Don't be afraid. 50%. Okay, 50%. Yeah, right answer. 50%. Okay. But 50% assumes that it's a normal coin, and that's an assumption, right? So now the tools of probability are so magical that you can start to question your belief, and the tools will take you in the right direction. So here, this is a Bayesian flip that I'm going to show you next. So here I have normal coin and a two-headed coin. Initially I started off at 100%. Okay, this is not a two-headed coin. This is a normal coin. And I'm going to just keep seeing 50-50 heads and tails. But after seeing 7 heads in a row, I'm not so sure. I'm going to be a little bit skeptical. So I'm like, I'm not sure. 90% is going to be a normal coin. There may be 10% chance it's a two-headed coin. If it's a normal coin, it's still a 50-50. And if it's a two-headed coin, 100% certain it will always be heads, 0% tails. Now, what happens if you see the next coin toss, if you see a tails? What is your probability that it's a normal coin versus a two-headed coin? What does your intuition tell you? What probability? What probability? Good. Very good. What is your name, madam? Good. Perfect. Okay. So I just applied the Bayes rule. And so this is saying that when you flip it, you now have a 55% chance of heads, not 50-50 anymore, because you have doubt in it. And you more chances of heads because you have 7 heads in a row. Okay. And now if you see tails, it's 100% certain it's normal because there's no, this is not a two-headed coin. Two-headed coin will never allow this to happen. But if you saw one more heads, then normal coin, it is 81%. Okay. So now I can go back and say, oh, I had started with 90%. Now I should believe it is 81% because I saw one more head. This is Bayesian updating. So now I make it 81% and I can do the same thing again. I toss it again. And the moment I see a tails, immediately 100% is normal. But if I see one more head, now it's 69% chance of normal. Do you see what is happening? At each successive iteration, I'm moving. My learning is getting updated. This is how the human brain wants to reason. This is the common sense of logic. And the beauty is with Bayes' theorem, you're actually seeing it work. That yes, now you have 69.5% chance of heads. You see one tail, again 100%, reset. But if you see one more head, now it's more likely that it's a two-headed coin than the previous one. Excuse me. Now, where does this connect to your world? So let me change this word from normal coin to normal machine. And defective machine. Like you think it's a normal machine, but oh, wait a second, something is happening. So this is one way of applying it. Now the problem with thinking of it this way is you need a clarity test. Like how do you know it's a defective machine? Is there any attribute? And you cannot say that the defective machine's only attribute is it's got a different distribution of heads and tails because that's not a clear, it's got uncertainty in it. So this is more suited for when you can clearly say, uh, let's say this is let's say this is machine A versus machine B, but you don't know which one it is. But from the observations, you can reason about where it is coming from. That you can do, provided these are clear, these exist, and somebody can tell you which one it is. Then you can reason it this way. So now I'm going to move to the continuous world of this. And the continuous world becomes even more interesting. Oh, this is read only. I guess I'm going to save this. We'll just call this data. So here I can choose. So this what this spreadsheet does is it sets up A/B tests if you want to compare something with something else. But let me ignore the testing part of it, the A/B part of it, and just look at one of them. So let's say your machine has some kind of characteristics. We already now. So if I say that they this is looking at long-run fraction of flakes. This is not going to work very well. So this should be the diameter of what is the machine called? What is the part called?
Or board diagram.
Bore. Diameter of bore. Okay. So we diameter of bore, let's say in centimeters, right?
Units.
So I need to do some adjustments to the mathematics to make it come out. Let me do it. Let me do it from scratch. Let me see if I can pull this off. So distribution. So so the beta distribution works on the coin toss metaphor. That means how many successes do you have in the this? So necessarily fractional. So you cannot do this on the diameter, but what you can do is say, is it in the tolerance or is it not in the tolerance? So you have to map that metaphor into the coin toss world. So what this is saying is, if you're within that plus or minus 0.5, it's a heads. If it's outside, it's a tails. And if you did it that way, then you can let's take that example. Then I'll give you one more way of looking at it with the actual diameter. Okay. So you could say that the number of heads. So let's talk about the toss equivalent. Toss equivalent is make the part, right? Part manufactured. And head equivalent would be non-defective, right? And you can either choose defective or non-defective. Let's say we said non-defective. Conform, okay. So conforming. So now this distribution is saying diameter of bore in no, this is not diameter of bore. Sorry, this is fraction of conforming parts. So we did 100. What fraction will conform? So now this is saying that that number, that long run fraction, let me be precise, I'm going to call it long run fraction. If you ran this for a long time, what is the fraction of parts that will be conforming? And this is saying we don't know anything about this. It's going to be equally likely all the way through. So my first question to you is, do you believe that? Okay, good. So by the way, most statisticians will try to urge you to take uniform distributions because they say, quote unquote, it's science. It doesn't make any sense. Engineering has to be practical because you do know this is not correct. So you know that it's going to be between. So what is your current long run fraction? What do you think the lowest would be? If I asked you the 10% chance of being lower than this, what would that be? What would it be? If you have 1,000 parts that you manufacture, and X is the fraction of conforming parts, how low could X be? Like there's only a 10% chance of being lower than this. How low could it be? I mean, if you've got a pretty good process, that number should be quite high, right?
Unconforming should be less than.
No, conforming should be high.
Conforming
Yeah, you want to talk about conforming or non-conforming? Which one are you more? So, no, which one are you more comfortable assessing? Non-conforming?
Yeah.
Okay. So let's change this to long run fraction of non-conforming parts. Okay. So what fraction, any lower than this percentage and you fall off your chair and disbelieve, you will not believe it. Like it's got to be at least this much. What is that number, the lowest number of non-conforming, fraction of non-conforming parts?
Less than 5% also.
Let's 5%. What if it's 4%? Would you believe it?
Sometimes.
What if it's 3%?
3% is too hard to
Too hard to believe. Okay, that's the test. This question and answer that I just did. This is the human conversational probability. Okay, so he says 4%. Oh, sorry. So 4%. Okay, and then probability is always assessed at the extremes and not at the, like if I go to 50%, I'll anchor you. So I want you to focus on the other extreme. How high is high? Any higher, you will not believe it. 99% non-conforming?
That is
No, non-conforming.
confirmed.
Yeah, how high could that be? 4% is the low end.
So, yes.
What is the opposite end? How high could it be?
Generally, 3-4 trials are there, we will be taking average of it, maybe 6%, 7% may not be acceptable,
What if it is 7%?
depending on working conditions.
Okay, you won't believe if it is 6, 7, but 6 you can believe, the highest. Yeah, okay. Okay, and then the middle, equally likely to be above or below this.
Median is
You want to take 5%, okay, you want to split the difference, okay. So 4, 5, and 6. Now, the beta distribution, so let's look at the beta distribution. So the mean of the beta distribution is defined as alpha by alpha plus beta. So the shape parameters, uh, so let me see, this is probably the time when I switch over to the whiteboard. Let's see if I can do this. And then variance, obviously not looking good. Mean is alpha. Okay, let's take a screenshot of this. Whiteboard. Good. And then beta distribution. I want the variance formula. So what we did was we got the percentile distribution, right? So these can be now mapped into this. No? There we go. Okay. There we go. It is working. I'm just trying to figure out how. So this is 25% chance. Did you say you said 0.4, right? And then 50% in the middle, 0.5, and 25%. This is 0.6. So the mean is half of 0.4 plus no, sorry, 1/4 of 0.4 plus half of 0.5 plus 1/4 of 0.6. The reason I chose 25, 50, 25 is this is the established discretization theory that when you look at the curve, this is the way, if you cut it at 10, 50, 90, then and you discretize into this kind of a tree, you can approximate it to the 25%, 50%, 25. And so that gives you a mean. So anybody wants to quickly calculate and tell me? 0.15. Right. Did I get that right? 35, 40, 50. The mean is 50. Yeah. So, and what is the variance? Variance is, right. Well, you know the, this is, so it's 0.5 square. I'm going on again. 0.5 square minus, no, no, this is E of, sorry, I got it wrong. E of x square minus ex the whole square, sorry. So, no, the square should be inside. This is wrong.
Yeah, it's square of each of them.
Come on now. Okay, at least end. Okay. There. So E of x squared is simply, it's 0.16 times divided by 4 plus, so it's just this thing, but square these terms. So anyone wants to calculate that for me? So this is, so what is it? 0.04, sorry? So this will be 12.5, 21.5, 25.5. Did I get that right? I hope I got that right. Yeah. So it's this number minus 0.20, 0.25. So it's 0.005.
Yeah.
So variance is, okay. So that's the variance and we got the mean. So now we should be able to talk about fitting these and finding what the alpha and beta parameters are for this distribution. So you have these. Let's go back. So we have to make alpha and beta the subject of the equation. So alpha alpha, right? And then mu alpha plus mu beta. Something like this. And then we have the variance also. So let's just say that's V equals And if you want to make this the subject of the equation, so variance equals alpha is mu beta times beta by 1 minus mu, and alpha plus beta square is mu beta plus beta divided by 1 minus mu square times alpha is mu beta by 1 minus mu plus beta plus 1. So it's this hairy thing, but we should be able to solve because we know mu, we know variance, we just need to find beta. So I believe we can take some help. I have to find it. This is Mathematica equation solving. Oh, I think there's an online one that where you can just put in the equation and it'll just give you the subject in the symbolic family. This one, yeah. Okay. So linear one. Oh wow. I can just give it to the system of equations. Okay, let's see if this works. This will be really cool. Solve. What are we solving? So we've got alpha divided by alpha plus beta equals mu. So A divided by A plus B equals M. And we know M, right? What was M? Mean was 0.5. And the second one is, I can just use this. Variance equals alpha beta. So variance was 0.005 equals alpha beta. So AB divided by alpha plus beta square times alpha plus beta plus 1. Okay, I think that's it. How do I go ahead and solve? Oh, it says solving it. Did it do something? Interpreting a solving. Yes, I want to solve this system of equations. Do I need the word solve? There we go. Okay, input interpretation, result. There we go. Okay, so I think we got it. Okay, there we go. This is what I was hoping for. AB is 49 by 2 and B is 49 by 2. So 49 by 2, so this is half, that's correct. And for 24.5, so 24.5 square divided by I think this is correct. Yeah, this is correct. Okay, so it solved it for me, and I did all of this stuff to get the alpha and beta. So the mean is, here we go. This is 24.5, 49 by 2, and this is also 49 by 2. So this is kind of the distribution that you give. So if you, yeah, it looks normal, it looks symmetric. Yeah. But the neat thing is it's shown in the beta. Now the nice thing about the beta is if I think this one's too complicated, maybe I should just do it from scratch. So the beta distribution, I can run the x's, say in over 100 of them, going from 0 to 1. And let me run, so alpha is 49 by 2. And beta is 49 by 2. And now I can say beta distribution is x. Use the shape parameters here. And I want as a CDF or the PDF. Let's do both. So this is true. Actually, let's make it more intuitive. So I'm just going to call this alpha. And I'm going to call this beta. And this one, I'm going to make it false. This is a PDF. So this is CDF and PDF. So this is your probability density function. You can see it's really narrow from 0. This should not go to 1.2. Let's make it stop at 1. There we go. So this is your density and your cumulative. So CDF, cumulative density, and your PDF. Now, this is the starting point of your observation. So let's say this is what you currently know. So what this is going to let you do is to do inference. So just like we did Bayes' rule, right? Bayes' theorem to update. Bayes had also worked out continuous probability, which you'll see in the previous lecture.
This will not happen. So narrow. Everything should be.
No. So now what I'm going to show you is now you start doing the experiment and you start seeing observation. How should you update this? Okay, because this is so narrow, right? Now, if I ask you that same question that we were doing earlier, that target is 25, right? So target is 25. And so low is minus 0.5 and high is 0. And I want to find out the probability just before we do the observation. What's the probability that you will meet this band? So then this is probability of x below y, something like that. And so this is, we can do the x lookup again. So I want to look for the x number, this, and where did it go? What's going on? Sorry. X lookup. Lookup array. Why is it in this sheet? Okay. Let me just close this one for a moment. You want to go to this is okay. Lookup value. Oh, okay. This is where okay. I want to look up for this value in here, and I want. Why is it doing that? One sec. I may have too many Excel sheets open. Let me just close them. There we go. Okay. I think it's working now. So this, I'm going to look and I'm going to find it matching. And what am I looking for? I'm looking for the CDF, the probability value. And I wanted to make a loose match. Oh, wait a second. Oh, and 0 if not found. There we go. From there. I'm saying this. No. So 24.5, it should give me this number. Why is it not doing that? So if I look at this, oh, that's right. I can't do 24.5. Sorry. No, this is what I'm doing here is wrong. The x-axis is going from 0 to 100%, which is the percentage of non-conformance. So, so I don't think you can answer that question, whether it will go below that. What you can do here in this is, if you start seeing the next batch, how many non-conforming samples there were, okay, sorry, you can get the confidence interval from this. So your 10th, 50th, 90th confidence, this you can answer. So non-conformance is, so I want to look up at the 10th percentile point, what is my X value? Yes, that you could tell. And return array, comma. There we go. There we go. So this is saying on the y-axis that, is this correct? 24.5, 25. So your non-conformance percentage is 40 to 60%. I think why does it feel wrong to me? You said 4, 5, and 6%, right? So it's not 40 to 60%. So what? Maybe we did something wrong here. When we were, oh, my mistake here. I forgot a 0. I put 40, 50, 60%, right? This should be 0.04, 0.05, 0.06. Okay. So this should have actually been uh, 0.05. And because it's all getting squared, so this is, so this is another two zeros in front of it, basically, is what I would just do. So we'll probably give the same answer, but with zero. Let's see what it does. Oh, look at that. It's quite different. 949 by 20, 18,031 by 20. Let's check if that works. Excel. Okay, much better. This is what you're talking. Okay, I think what's going on. Okay. So now if you look at the 10, 50th, 90th, it's you can see it's going from 5 to 6%. So now why is it not 4%? That's because the beta distribution is an imperfect fitter. Like what I just did, the beta distribution has two parameters, mean and variance. And you gave me three inputs. So three inputs, you're going to lose some information. That's why the meta log is a much better way of doing it. But the beta distribution allows you, this is the classical probability theory. So now let's say you see some data, and in your next set of experiments, so the way you interpret this is, so number of successes is alpha, and number of tosses is alpha plus beta. So whatever the distribution that you gave is the same as though you tossed, you saw 47 heads out of 949 tosses. That's what you actually said. So now when you have this information, this is very powerful because now, let's say you do the experiment or you run some batches, and let's say new successes. And we fixed the issue. The issue was one missing zero in front. So now you can see that it's a very narrow distribution over here between 4 and 6%. Okay. So and 10, 50, 90 is like this. The reason it's highish on the 5%, I was just explaining this, that beta distribution is a two parameter distribution, whereas you gave me three inputs. So you're going to lose some information when that happens. But be that as it may, I can interpret the alpha and beta very naturally as the number of, you saw 47 successes out of 949 tosses. That's how the distribution is fitted to your assessment. Let's say now you run another 1,000 batches. And in these 1,000 batches, or 1,000 pieces, 1,000 pieces, how many defects do you see? Let's say for fun, you see 100 defects, which is very high, right? So what happens here? How should you update this? So then this is total successes. This is the beauty. This is why everybody uses this for Bayesian updating in the continuous world. And total tosses. So this is your collective knowledge pool now. So total what you knew before and what you know now, you see this over this. So now you have a new alpha, which is the same as this, and new beta, which is this minus this. Okay, so now using this, I can create a new distribution. So let me just, where should I do this? Let me copy it, yeah. And here, this is, I'm going to call this new alpha and new beta. So this is so for those of you who attended the previous workshops, what I'm creating right now is the posterior distribution. So this here was the prior distribution. So let's plot it and see what it looks like. Barely see anything there. And I think this is, there we go. So one of the challenges with this is if you PDF, this is one of the reasons why I asked you, how do you interpret the y-axis of a probability density function? You can't. There is no interpretation. And as long as the area sums to 1. That's why when I plot them together, you can't see 1 because some of these numbers are so small. So you need to see them. There's some tricks of how you plot them so you can see them. So I'm plotting them separately now, but I need to superimpose them. So I'm going to just for now do these tricks. The other trick, of course, is you use 2 axes. That way you can do it. This is not easy to read, so I'm going to just make this all white background. There you go. And 0 to 1, 0 to 1. There we go. So it shifted a little bit to the right. That's because you saw so many issues. This one, though, you can add the second one because the y-axis has interpretation. The y-axis is the probability. This is the prior. And let's add the posterior here. There you can see that it shifted to the right, which means your non-conformance has gotten worse. So what if now we can play with this? So you say, okay, so I'm going to mark this as green so you know to change this. So what if it's not 100, you saw 500? So now you're in pretty bad shape here. And so this is the new, let me show the new non-conformance as well. So we want to read this as well. And read this from this distribution. Oh, sorry, I need to read it from this one. This is I6, yeah. And where's it coming here? Ah. Yeah, there you go. So you can see that if you see results like this, 500 out of the next 1,000, your distribution is now 27 to 30% non-conformance. But if you saw only 10 off, then you're at 3 to 4%. Now you got a better non-conformance result than you did before. So this is how your knowledge. So now you can see that the graph is shifting to the left or to the right. Right? So this is how you would engage in that language of uncertainty and get conclusions that are justified. So this is the beta distribution. This is the classical approach to doing this. The new approach of doing this is going back to the main meta log distribution. Let me see if I can open that one. So in the meta log, that is a more accurate match like this. Remember we started here, 23, 25, 26. Here, what you would do is you would get the new readings and you would get the new 10, 50, 90. Then you would ask yourself, how do you want to combine that with the old? And so how much weight do you want to give to the new data versus what you already know? And then when you combine them, you'll get a new percentile, which will immediately match. And that's like a trivial operation. And this will get updated. So those are two different ways of doing it, two very different ways of doing it. This one's more modern and but it requires a little bit more thinking. This one is a little bit more automated, but you will lose some fidelity, but it's both will get you in the right direction. Right? Let me pause here. This is a pretty deep dive. How is this sitting with you? I mean, I went from first principles and derived the whole thing to the end. For both of you, how any reactions?
Not understanding.
Which part?
No, what's your question?
Oh, my question is, now that I've shown you from beginning to end, what is your reaction to this? Like talking about how to engage with reliability with foundational principles of progress.
Calculations and setting the machine. This is 1 minute job. Enter the data.
Yeah.
And see.
Yeah.
Whether the skill aspect or confirming. So that they can, in 5 minutes we can conclude that they want to take data.
So what is the decision? Yeah. Go ahead.
Percentage of unconfirming onto setting, so that you can see the changes, set aspects, so that the time cycle can be reduced. Cycle time,
Right.
machine aspect.
So you could take this all the way to calculating the time cycle as well, right? From the when you have the probability distribution, you can get a sense of the range of time it will take. Yeah.
Cycle time can be reduced.
Is this helpful?
Yes,
Yeah,
of course. the
Okay.
effect is-
Okay. Okay, we got into this very deep. Yeah, so I'll share this Excel spreadsheet. You can see all of the people. Yeah. Okay, okay, yeah. Yeah, so this is all Excel first principles. I'll give you the spreadsheet, and this is the example you can look at. Let's see now. I think we're almost at time, so I have.
Excel also.
Yeah, no, this is yeah. This is just the beginning. This is like a whole universe. Once you get into it, it's a different language of thinking, and you can report and use it in decision theory as well. So let me see. I have maybe 8 minutes, so I'll say a few things. We're just getting started. Like let me show you this. So my colleague Anuradha Chandrasekhar, she is going to also come and talk about life after engineering. She was in my batch in computer science, and also we were both students of Dr. Venkataram. And she will do this interactive workshop this will be for students and anybody else, I guess. So the idea is, I guess she can come. She's local, so she can come on. She can do hybrid, but I'll let her talk about it. But this is just to give you an advance glimpse that this is coming up for people. Yeah. November. Okay, so maybe she will decide the date based on that. And this, when you have really different choices, like you're not really interested in engineering, or you want to go to a large corporate, everybody's happy, or join a startup, or go teach, or do research, or whatever. How do you navigate this? So that's the talk she will give. And I also wanted to end with, let's see. I know since we're doing this under for RV Sir's memorial, I promised Ashwath sir we would talk a little bit about RV sir. Yeah. So some of us just put together some photographs. And I know Ashwath sir gave me a photograph which I should put into this one. So the reason I'm here and spending this time is because when I was an undergraduate student, RV sir, I mean, I spent a lot of time in the mechanical engineering department, believe it or not. I still remember I just walked over that time. Jagat sir had created the CAD. I still remember this one. Somebody's mic on. You might want to just turn your mic off. Yeah. So there was just one computer, a multimedia computer, and I just showed up and said, "Hey, if you have you need virus scanning help, then I can help check." So he said, "Yeah, come to the lab all the time and just make sure we are safe." And so I would spend a lot of time in the mechanical engineering department and made friends with the professors and met RV sir. And RV sir was very instrumental for not just me, for the entire batch in mentoring us, guiding us, shaping our thinking, helping us think deeper. And we had a lot of fond memories. So he, later on we found out, he never had kids and we never knew why. But his wife, in his memorial service, she told us that when they got married, they decided very intentionally. So they decided very intentionally that they wouldn't have kids so that RV sir could support the students full time. And his wife is a gynecologist. You'll see her now. I think she'll come. Yes, and they also have yes. So she could focus on her patients and he could focus on his students. So that was remarkable for somebody to make that kind of a commitment to us. And he came. He could, he was an IIT PhD. He could have gone anywhere, but he chose to come here because this is a place where he felt students could be influenced. So yeah, he did his BE in UV and MTech in IIT, and did his doctorate in droplet combustion. Uh, and he stayed in BIT for 15 years. Was in PESIT for a brief while, and then went to a couple of other places. And he was one of the founding faculty of S. Vyasa, which I found out only much later. And there, at that time, I was giving a lecture on probability in S. Vyasa, and I was like, "Oh, you told me he's one of the co-founders," and I was shocked. And he was in the audience when I was teaching a workshop similar to this, and RV sir was asking the most questions, the hardest questions, which was great. And so I really miss him. And yeah, Lata madam will be here. She'll talk to us some more. And he was great at cooking. Whenever I went to his home, he just loved feeding. So just miss him very much. There's some pictures. In the last few years of his life, he had an aneurysm, which had left him paralyzed on one side, so he couldn't move much. But I met him even after that, and he couldn't speak, but he still made sure he would feed me. And that was just his generosity always. I have one picture of him. It's very blurry from our college days, which Ashwat sir just sent us yesterday. Try and see if I can show it here. Give me 1 minute and I'll be show it here. This was a college festival. I think Ashwath sir had mentioned we had done, and this was, I think, the last day. And there's RV sir over here.
In between that semester.
Yeah, right here. Second. So, yep. Thank you, everyone. Yeah.
Third one, right?
Sorry. Yeah, I'm there. This is me. This is me. Yeah. So 20 years back. 1997.
Yeah, Somik, there are many other people in this photograph. This is one of the photo we took, I think, during the Mruga Krishna or some college
right.
day after that.
That's right.
So the extreme left is Bachu. He is now a popular playback singer. And number two is Dr. RV, and he used to be there in all our activities as a supporting, motivating factor in most of our activities. And of course, the third with black suit, blue suit is you, who is heading the most of the volunteering work during that time. And it is me. And then next is Vidya, and Vidya is now running a school, drama, theater, and other music school and other things. And the next one is Annapurna. Annapurna is now in Goldman Sachs, and she is also a technical writer for many of the companies. And all of them, many of them are there. The photo is little blur. So there were about 300 plus volunteers during that period for the placement and training center, and it was a great experience to work with all of you. And I'm very happy all those who are involved in that period are all doing well in your careers. I'm very happy for that, and for the success of all this. And Dr. R. Venkataram is one of the motivational factor, and we all remember him and we miss him very a lot. And this is the first effort of conducting the memorial lecture in his name. And in the days to come, I request the mechanical department to take initiative and carry forward this memorial lecture as and when necessary, and at least once in a year. The memorial lecture series should go on, and many of our alumni and any other subject experts should be speaking in this lecture series. I'm very thankful to Swamik Raha for taking the lead in organizing the first memorial lecture. And we have already discussed several other programs under RV's name, and I'm sure in the days to come we will be launching some more programs. Thank you very much, and I thank all the participants. I hope the last 3 days, the magic of probability and decision analysis, one of the most important topic
Nice.
and Somik being an expert experience. I was also on and off what exactly it is, and I started appreciating. I hope the participants have got some from this program.
So I think we're having some trouble with your connection.
Hello?
Now we can hear you.
Okay. You didn't, last 5 minutes I spoke something. Did you hear?
Most of it.
Okay, fine. Okay. Good. Now the session is over?
Yes.
Okay.
Any
Participants.
participants, any reflections, any closing thoughts that you want to share from, we did a lot of deep dive today. Any reactions? If you want to take the floor, please unmute yourself and go for it. Or you can also type on the chat.
I think they can unmute and speak if anybody wants to talk. I see some
morning, sir.
faculty from computer science department are also here. Somik is basically from computer science, and he worked on artificial intelligence way back in 2000 or 95, between 95 and 2000. He worked some projects on CDAC, and he participated in IIT Bombay, and he won some prizes there. So he has got a very serious student, very actually working on various innovative projects from day one, and went on to Stanford, and he has got a lot of experience. I request the computer science faculty to make use of his expertise, and maybe you can exclusively ask him to give some talks on computer science and artificial intelligence or information science related areas in the days to come. I hope you will oblige. Since he is also working in a corporate, he needs to take some permissions before he deliver any talks. So well in advance, you can inform him and take some support for the development of the departments.
So I think somebody was speaking in the audience.
Yeah, good morning.
Yes, we can hear you. Go ahead.
Myself, Dr. Maya BS. I'm working as assistant professor in the computer science department of BIT. I'm very thankful for organizer for this lecture series with the name of Dr. R. Venkataram on the title of The Magic of Probability and Introduction to Decision Analysis. I'm very thankful to the Dr. Somik Rao sir. It's a very excellent PPT. I am not heard. I attend so many workshops, but I never thought what these type of PPT with including Kannada and English. And you are giving that assessment for that also. I so much as I liked. I learned that understanding level of probability from where it is come, where you are applying, the real time applications for that. We did for the problems for conditional probability and for the hemophilia, lung cancer, and as whatever you are currently we are talking about COVID antibody test also. And we thought we don't know how to apply for probability, but I am from CS department. Just I learned the concepts of probability as while studying for PhD subject as well as my and BE. But now I get so much of interest to do for that, how to do that probability subjects also. Mainly I am interested in the mathematics, but unfortunately I am in CS department for that one. I am hope it I am learn with the maths also. And the session is also good for the second day. Decision analysis, we should be know that what are the qualities of decision quality, and we told the 6 decision quality to how to get the decision and what is the difference of outcomes also. And heartful thanks to the once again sir and Rupa ma'am for giving a good lecturers from these sirs. And can you please give one more session on CS department also? I will inform to our HOD ma'am, Girja ma'am also, and please conduct one more lecturer series in our department for that machine learning for any other topic, whatever your domain will involve. And thanks to the entire mechanical department and skill development center and who are involved in that lecturer series. Thank you very much, sir. Thank you, sir. Thank you, ma'am.
Vinay sir, please give your feedback. Dr. Vinay. Ma'am, Dr. Vidya ma'am.
Hello, am I audible?
Yes, ma'am.
Yeah. Again, I am always participating the very new topics of FDPs you are arranging. Thank you very much for that, Rupa ma'am, and also the institute. I congratulate everyone, those who worked to arrange this such a type of FDPs of your college. Thank you very much, sir. And also I am very much pleased with the knowledge the resource person shared with us. Thank you very much.
Rajamani sir. Vijayendra sir. Anybody have an interest, please give one or two feedback. Sir become is asking every day, what's my
Hello, myself Tejaswini from
how's
Computer Science Department, ma'am.
relevant to
Actually,
the
I would like,
yeah.
I would like to thank to the organizer as well as the speaker because the session was very informative and interesting also. The polling made us very interesting in between the sessions. I would like to once again thank for the organizer as well as the speaker. Thank you.
Any other participants wish to share your feedback?
Good morning, sir. Myself, Nikita, Assistant Professor, Department of CSC. The session was very informative, and the polling, both in Kannada and the sir is used to ask the questions in between the attendees are very informative or not. Really, it was very helpful, sir. Thank you.
Thank you very much, ma'am, for your feedback.
Thank you, sir.
Thank you, everybody. I really enjoyed coming here and doing these workshops. So yeah, just good luck with everything, and I'll send the slides, the material to Rupa madam, and she can send it out.
Participants means our colleague for our college and outside the college.
Can we be heard? Are people getting the idea?
Yeah.
You might want to speak from here.
Thank you very much for every participants means our colleague for our college and outside the college to giving
Thank you.
a support to conduct successfully for 3 days international lecture series and prob.
ನಂದೇ ಅದು ನೀವು ಅವಾಗಲೇ ಮಾತಾಡಿದ್ರಿ
Please go ahead.
My voice only. Yeah, once again, thank you for everyone there inside and outside college. Some faculty members are coming outside Karnataka also. And we are expecting same encouragement further future also in for all workshops. And then we are heartfully thanks to our Dr. Soumik Raha. He's taken so much interest to deliver magic of probability and decision analysis. We learned a lot of things. Even though I'm a mathematics, we learned new things to how to teach the students very attractively and interestingly that probability. I think 3 days is not sufficient. We are expecting planning to conduct 5 days fully along with the hands-on what he showed today for tools, how you take a simulation for probability to take a decision in the mechanical like that. We are expecting in each field, say civil engineering for one example and electronics.
ಹಾಕಿದ್ರಾ
civil engineering, mechanical engineering, like that, computer science, every topic, they suppose they're going to show one simulation that's useful for everyone. We are planning to that. We have to conduct for 5 days for the simulation part. Once again, thank you very much for everyone. And also we thank to our principal and also Principal Dr. Ashwath MU sir, and also Vice Principal to give opportunity to conduct 3-day webinars for this webinar. Association with the skill development and mechanical engineering department. Once again, we thank you one and all. We are expecting in the further future webinar also. Okay, thank you. Thank you, sir.
And maybe all of you can switch on your videos and take one group picture for the record purpose. Somik, please switch on your video.
But we can all be.
Shekhar, please take a group picture.
Sure, sir. You can take a. You can take a screenshot here. Yes.
Sir, please.
Okay. Think. Is everybody visible?
Yes.
Okay.
Yeah.
You can also check how many of them are listening.
Okay, I think I got it. I will just WhatsApp it to you. Okay, I just sent it. Oh, is there more people now? Okay, there's more people now. Okay, one more. Okay, I sent it. Thank you, everyone.
Thank you.
Already sent it. Yeah.